Welcome to this series in group theory. Last time we looked at Fermat's little theorem, which says that if p is a prime and a is any integer, then this congruence holds. And a special case is that if a is relatively prime to p, then in fact you can say that this congruence holds. And today we'll be looking at a generalization of it. Before that, here is a set of problems. Basically, this is a guided exercise giving an alternate proof of Fermat's little theorem. Okay. So we'll introduce the torsion function. So we have some positive integer chosen. Then this symbol denotes the set, or not the set rather, the cardinality of the set of all those integers which are first of all in this range, and their GCD with n is equal to 1. So all integers relatively prime to n, which are between 1 and n, where 1 and n are both inclusive. So what is phi 1? Phi 1 is just 1. And I don't want to say much about that. What is phi 2? So 1 is relatively prime to 2, but 2 is not relatively prime to 2. So this is also equal to 1. Phi 3, it's equal to 2 because 1 and 2 are both relatively prime to 3, and of course 3 is not. Phi 4 is again 2 because 1 and 2 is not relatively prime, 3 is, and 4 is not. So therefore phi 4 equals 2. Alright, more generally, suppose we have some prime p, then this is equal to p minus 1. And let me just show this in an example. If p equals 5, then 1, 2, 3, and 4 are all relatively prime to p, and you can just easily see that this holds in general for any prime. More generally, if you have prime power, p is a prime and k is some positive integer, then this is equal to that. And the reason is very simple. Let me explain in the case of k equals 2. So let me explain for phi p square. So note that if I want to collect the numbers which are relatively prime to p square, and in the range 1 up to p square, I will be writing all these numbers. And then there will be a p, and then p plus 1, 2p minus 1, then 2p, and then 2p plus 1, and this will go on till p square. And I want to delete those numbers which are not relatively prime to p square. But since p is a prime, not being relatively prime to p square is same as not being relatively prime to p. Right? So what I'm saying is the following. I'm saying that GCD of a comma p square is 1 if and only if GCD of a comma p is 1. Right? Because if, for instance, suppose this GCD is 1 and you want to conclude that GCD is 1, you can use Euclid's theorem, for instance, because what you'll get is ax plus py equals 1 for some integers x and y, and then, well, you square both the sides, then you get a square x square plus, well, some integer times p equals 1. So I hope you see that, which can be written as a times ax plus p times some integer, who cares what that is, equals 1. And this implies that the GCD of, this I messed up. Sorry, I completely messed this up. So you square both the sides, you get 2apxy plus some p square times y square. This is equal to 1. So now you take a common here, and here is some integer, we don't care what that is. So this is equal to 1, and now it's clear that the GCD of p square and a is 1 because GCD of p square and a divides the left hand side because it divides both of these guys. So it divides 1, and hence the GCD is 1. So if this GCD is, if this GCD is 1, then that GCD is 1, and you can do the reverse direction much more easily. You don't even need all the squaring business. Just apply Euclid's theorem and you'll immediately see it. Or you can see it in other ways. Anyway, so just realize that. Again, I made a mistake. Just realize that. So all we are looking for in this whole set is those integers which are relatively prime with p, and we want to kick out those which are not relatively prime to p. And what are the things that are not relatively prime to p? Those are things which are divisible by p. That's because p is a prime. So we just want to kick out those things which are which are divisible by p. So since there are, every pth guy here is divisible by p, then 2p, and then 3p, and so on, there are exactly p square upon p things which are bad, which we want to throw out. So after we throw them out, we will be left with these many things, which is p square minus p, which matches with what we wanted to show, because k equals 2, so this matches. And you can generalize this reasoning to any power. Anyway, so this is clear. And now here is the Euler's theorem, which says that if n is some positive integer and a is relatively prime to n, meaning GCD of a and n is 1, then this congruence holds. So here phi n is, again, as we just defined, is the number of integers between 1 and n and are relatively prime to n. And this is an immediate generalization of Fermat's little theorem, because if n were a prime, then as we just saw, this becomes n minus 1, or rather, let me say n equals p of prime. Then this becomes p minus 1, as we just discussed. So a to the power p minus 1 would be congruent to 1 modulo p for whenever a is not divisible by p. So that was so this is a generalization of Fermat's little theorem, and the proof is ditto same. What we'll do is the following. I'll not do the full details. So let S be the set of all these. Let me use maybe I. I don't like I, but anyway, all these folks which are relatively prime to n. And of course, then phi n is the cardinality of S. So phi n equals cardinality of S. All right, and here is again the same thing. So Fa is this map which takes S to, again I will write S, but that needs some justification. What is this map? This map takes little x to the remainder when you divide ax by n, just like in Fermat's theorem. So this notation here means take the remainder when ax is divided by n. And one has to just realize that indeed this guy lies in S, because this thing lies in the set 1, 2 up to, or let me just say 0 up to n minus 1. But since x and a are both relatively prime to n, so is ax. And therefore, the remainder that you get once you divide by n is also relatively prime to n. And therefore, this guy lies actually in S. So just realize that this is a well-defined map, and then you can just do the exact same reasoning as one does for Fermat's little theorem. So continue as in Fermat's little theorem. In the proof of Fermat's little theorem that we gave the last time. Discussed the last time, and that's it. That's the end of this proof. And with this, I hope I will be done with the elementary number theory part. I don't know, maybe I'll add more lectures if needed, but for now I think this is the last lecture in the quick recall of elementary number theory, or rather a primer in elementary number theory, which we have done because I want to show applications of group theory to number theory. So all of these theorems that we discuss in elementary number theory can be either viewed via group theoretic means or sometimes even proved via group theoretic means. Certainly Fermat's little theorem has a very nice and very simple proof using group theory. So does Euler's theorem, and the perspective that we get using group theory is much more, to me it's much more beautiful, and it's notationally also much more pleasing, I would say. Although I really like the congruence notation, but you'll see what I'm talking about. Alright, so as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.